Therefore, everybody has the option now of agreeing to this or leaving the meeting. Very good. Okay. Well, I think that we'll start out by looking at the unanswered questions of last time, where I made a mistake in posing the question. Okay. I need to button up here. The dress for this is business formal for classes. And none of you guys are in business formal. Okay, that's okay. We'll go ahead and proceed. So let me share my screen here. I wanted to point out something last time that I looked at, and I don't know if any of you were following this, but we said that David won the tic-tac-toe problem by these four. Yet, if we look over here, Adam had a 0, a 0, a 0, a 0, and a 0. So he had 4 in a row also. Now the question is who got it first?
Yeah, we kind of both did it on the same round, but I think he got it first because he went first.
Oh, he did. Okay.
Yeah.
Okay. So it wasn't a tie. I appreciate you clearing that up, because the last thing I want to do is go back and look at that video again. Okay. So, okay, I wanted to point that out, that it was a near tie between David and Adam, but Adam gracefully has said that he was second. Okay, let's look at these problems here. Hopefully you see them. I think we can start with, I think we finished 28. Let's go with 29. And we have 3 people here. Let's do it by volunteer. Anybody like to volunteer to do 29? Oh, everybody's jumping up and down. If not, I'll have to get out my random number generator.
David's raising his hand.
David, do you want to? Somebody said that. Quick, David's raising his hand. I don't want to do it. Okay, I don't know who said it, so that's okay. Okay, David, go ahead and dazzle us. You have screen sharing privileges. You have to unmute yourself. You're muted.
All right. So just a moment. No.
Oh, you have to switch to your overhead cam. By the way, I bought an overhead camera. Here's my overhead camera. You like that? This is for documents, except I'm having problems putting the driver in. So I'm going to figure that out in the next couple of days when I have some time.
Okay.
Okay, go ahead.
I think you need to stop sharing before I can start.
Okie dokie. I have stopped sharing.
Okay. All right. Yeah. Which program? Which problem?
29, I believe it was. Isn't that right? 29.
Okay.
No, wait a minute.
Yeah.
No, it wasn't. Wait a minute. No, it was 29. I'm sorry, 29. Okay, go ahead.
All right. So if a signal is sampled at a rate of 2W, which is greater than 2B, then the sampling theorem can be written as this equation.
Good.
And
you've learned not to sit there and read the equation.
Yeah.
Excellent. Okay.
We know that x of t can be written in this way, and if the transform is band limited, then multiplying it by a rectangle function will make no difference.
By the way, what do we call that in signal processing when we multiply it by any spectrum by a rectangle?
Would you be making it a band limit signal?
I'm sorry, something beeped while you were talking. Do you make it a what?
It makes whatever function you have into a band limit signal.
Yeah, it does. But I think, no, you're totally right. But I think a more conventional saying is that you performed a low pass filter.
Okay.
You're performing a low pass filter when you multiply it by a rectangle function, right? Because you're prohibiting frequencies outside of the band from getting through. And many times in signal processing, a signal is put through a low pass filter and a brick wall low pass filter. What do I mean by a brick wall low pass filter? I mean an actual rect. Because many times if you're trying to do stuff in real time, the low pass filter is kind of gets out here, it wiggles at the edges and then comes down and wiggles down here. And it really doesn't cut things out totally with 100%. But if you're doing it with DSP and you have the entire signal stored, you don't have to worry about that. Okay, go ahead, David.
Right. So, yeah, so we can turn this into take this from Fourier domain to time domain, and then yeah, and then put and then combine this with this equation, and then did some notes confirming that making sure I understood the equivalence, and I did the most abstract form of this transform.
Yeah, this is good because what the equation that David wrote down has both the shift theorem and the scaling theorem concatenated into a single expression. So it might be easier to remember this expression than it would be to remember the shift theorem and the scaling theorem individually. Go ahead.
Yeah. Okay. So then I so then I took this part of this expression and turned it into the time domain, and then simplified that and confirmed that I got sync of the argument we had at the top. So then I started over. X of t equals this, what we got directly from what was just given, and then combined the sinks using the what we got from combining the rectangle functions, and then yeah, just simplified all the expressions and got the desired expression.
Yep, that works. Thank you, David. That was pretty good. Could you stop sharing if you would?
Yeah.
Yeah, this is a very interesting equation and a number of issues. I want to illustrate some things by drawing pictures, which I always think is good to do in such cases. So let me share my screen here, at least with a whiteboard. I think what David just showed. Okay, whoop, wrong pen. I was drawing on my sketch pad. Where did my pen go? Where did my pen go? There it is. Okay, there we go. So he said that x of t is equal to r times the summation over n of the samples. The samples are sampled in excess of the Nyquist rate times the sink of 2bt minus Rn. Now this reverts if R is equal to 1. In other words, W is equal to B, the sampling rate is equal to the Nyquist rate, then it reverts to the conventional sampling theorem, right? And for R is equal to 1, we had the, I think it's just an interesting property. Now let's see if I can draw a straight horizontal line. That's pretty good. We have all these samples as a function of t. And notice this 2b illustrates how far the sinks are separated, right? The 2b figures out how far they are separated. And what we found out was just wonderful and beautiful, that the sinks for each one of these samples came down and went through the zeros of the other samples. And so this sink kind of came down. I'm trying to do it as a dashed line here into here and here, so that if we knew that we added all of these up, whatever the underlying signal was that went through all of these samples, that's the underlying signal that goes through, that interpolates, if you will, that all of them would pass through the points that were sampled, right? Now, what happens if you oversample? Right here, the separation between the points is 1 over 2b. What happens if you sample faster than the Nyquist rate? Let's suppose, for example, R is equal to 0.5. What does that correspond to? That corresponds to sampling at twice the Nyquist rate, right? Now, if we sample at twice the Nyquist rate, then these sinks are exactly the same width. They're stretched out the same because it's still 2bt. That dictates how much you stretch these out. So what happens then is that the value at the origin, if you can think of the value at each sample as R times X of N over 2W. Right? That's kind of the new sample. So in this case, the sample would be at 1/2, but the sink would be much bigger. It'll be the same stretching as the sink did over here. In a similar fashion, the sink here would be at this point, and we would have interpolation which goes like this. So you can see something interesting that happened, this beauty of just interpolating the signals at the individual points, giving the interpolated signal exactly at those points, we don't have anymore. In order to get this point, we have to add up the sample here. We have to add up a little of the contribution of the sample here, a little bit of the contribution of the sample here, and then lo and behold, when we add all of those ups, it gives us the corresponding interpolation that we need, okay? So again, we don't have the sinks going through the zero crossings of the samples anymore. And the value of the function at this point in this accelerated sampling is determined not only by the sample at this point, but by samples of adjacent points. Isn't that weird? Okay. Do you how many understand? How many would like more elaboration? More elaboration. Okay. Let me see if I can draw a better picture than that. In fact, let me go up here and erase this thing. I have such a sense of power here. Unfortunately, my jiggling here, oh, they have lines here. Okay, that's good. Oh, look, I can draw a straight line. This is much better, right? Okay, here is the axis. And they have little, well, that's not a very good line. There we go. Do they have little dots that you can draw? Yeah, they do. Okay, so we have a sample here, a sample here. What happened to my first sample? Oh, okay, there it is. I'm not going to do that. I'm going to do something else. We're first of all going to redo at probably a nicer rate. What happens at the Nyquist rate? We're going to have this sample coming down, this sample coming down, this sample coming down. And I know I can't draw a vertical line. I'm doing the best I can. Okay. See, this is interesting because I don't have a touch screen, so I'm drawing on this pad and trying to watch what the pad does. So we have these samples. Suppose that this is at the Nyquist rate. In other words, what I'm saying here is that 2W is equal to 2B. So this is the conventional sampling theorem. As we saw before, the sink from this sample would be a nice sinky interpolation function here. So you can see that this interpolation function, this sink interpolation function, makes no contributions here or here or here or anywhere else. The only place it makes a contribution is at the origin. All of the other contributions are totally zeroed out. And it's the same with all of the other sinks. The sink here, for example, comes down and goes through all the zero crossings, okay? So we see that that is the case. Now, this is the sink of 2BT times x sub 0, whatever that value is, okay? So that's the contribution of the sample of the origin to the entire interpolation formula. Interesting, right? So now let's look and see what happens if we sample in excess of the Nyquist rate. If we sample in excess of the Nyquist rate, then the following happens. We get a sample here, and the samples are going to be closer together, right? By the way, I'm not trying to do the same signal. I'm just doing another signal. Pay no attention to the size of the boxes. They're all supposed to be samples, okay? And so we have all of these samples here. I wonder what stamp is. Oh, that's interesting. Okay. So we have all of these samples, and each one of these samples is such that the separation between them is 1 over 2W. These are supposed to be equally spaced. I'm doing the best I can. Whereas up here, the separation between the samples is 1 over 2B, right? And down here, the separation is 1 over 2W. Now, according to the sampling theorem that David just derived, we don't have the sample. We have the sample times R, right? So for example, if R is equal to 1/2, means that we're sampling at twice the Nyquist rate. That means that the sample at the origin is sampled at R times that value. So this point here would be equal to R times x of 0. And if we put the interpolation formula, the sink of 2bt, which is the contribution just to the 0th order sample, notice this sink of 2bt is exactly the same as this sink of 2bt, right? They're exactly the same. So what happens is this sink function comes out, and it no longer goes through the 0 crossings of the other samples. So we have a similar thing that happens here. This thing has a sink of 2bt. It's the same 2bt, or the same sink as we had before, except it's shifted over a little bit. And we see that all of a sudden, the sample at the origin has an effect on the sample at 1, right? Because of the overlap. And so when we get, in order to get the sample at the origin, we not only have to add this point, we have to have the contribution of this sink, this sink, this sink, and this sink. So they're no longer independent of each other. This is where the dependence comes from that allows us to restore lost samples, because they're no longer independent of each other. They're dependent, and we can restore lost samples. So hopefully that clears things up a little bit. Okay? That made my mouth dry, so let me take a sip of a refreshing beverage. I got that from a Woody Allen joke. Woody Allen had a joke. It says, "Men can be desperate. Men will kill for food, and also occasionally for a refreshing beverage." And the reason that's funny, I think it's funny, is because you never hear the word refreshing beverage used outside of a television commercial, ever. It's always refreshing beverage in the commercials. So I like to use that. Any questions on this at all?
I have an observation. So
Yes.
in the second example, if we miss one sample, we will take the part of the other samples and just multiply it by 2. So we get the original.
Well, it turns out if R is equal to 1, you can. And in the restoration formula, which we're about to derive, indeed, that comes out as the case if R is equal to 1/2.
Okay.
We add up all of the other samples, and we multiply by 2. Yep.
Okay.
That's an interesting observation. But this, again, is just for an example for R is equal to 1, for when we're sampling at twice the Nyquist rate. Okay, with that, let me stop sharing my screen. And I will share my screen again. And we will go back to this, and we will go to, let's see, I guess a 30. Okay, does anybody want to do 30 besides David? He's put in his chops already.
I'll do it, Dr. Marks.
Okay, who said that? Aiden?
Aiden.
Okay, Aiden, yeah, go ahead.
If you'll stop sharing, I can share mine.
Oh, you're right. I'm sorry. Yes, yes. Very good. Okay, you're all set.
Okay. Okay, so
Okay, you're actually doing 30, which is fine. Go ahead and do 30.
oh really? It's not. Is this not the last one?
We weren't doing the last one. Maybe I misspoke, but I wanted, go ahead and do this one. This one's great.
Okay.
Because this one was the most difficult.
Yeah. So easy, right? And so so I started by setting t equal to 0, and so the t on the right goes to 0, and then obviously you have this over here, and then you can split up the summation into where x is equal to 0, or where t is equal, or excuse me, where n is equal to 0, and where n is not equal to 0. And I accidentally put capital X here. I just was getting kind of lazy with my notation. That's still lowercase.
That's okay. I can't tell the difference. So
Okay, good. So when n equals to 0, this is what you get. You still have to keep the r in front. I'd forgotten that, which is why I squeezed it in here. And then your n goes to 0, so you have x of 0 times the sinc of 0. And then you have x of 0 on both sides now. So I wanted to move x of 0 to the left. I factor out x of 0. And then I divide out the 1 minus r sinc of 0. And the sinc of 0, unlike like 1 over x, when x is 0, it's like undefined and the limit is undefined. But with sinc of 0, the limit as x or t approaches 0 is 1. So I just said it was 1.
yes.
Basically. And so that's how you get this. The sinc of 0 just becomes 1, and you get that r over 1 minus r that was given in the homework assignment.
Yes, exactly. And you can see this, and by the way, the sinc of minus rn, sinc is an even function, right? So therefore you can put the sinc of plus r in there if you want to.
Yeah.
Okay. Which is what we want. Okay, so that, yeah, no, that worked out very good. Okay. Let's see. So let's see. Yeah, who would like to do 30? See, I think Aiden, you grabbed this one.
Yeah.
You grabbed 31.
Everything you were just talking about, it made sense, but I was kind of confused at first because I thought you were talking about number 30.
Okay.
But and then yeah, I was confused. I get it now. Yeah.
Well, that's totally okay, because I think the 31 is a more difficult problem than the 30. And again, you mentioned this, Aiden, but what happens when r is equal to 1 here? Well, you have something over infinity. It becomes a meaningless equation.
Yes. Yeah. And you can't get your sample.
And then if r is equal to 0.999, which means you're sampling just a little bit above the Nyquist rate, right? As r is equal to 0.999, then you have a 1 over a very small number, the reciprocal of which is a very big number. And any sort of error that you have is going to be multiplied by that very big number. So this is an idea of something which is called, maybe I'll talk about this a little bit, because this is very important in communication theory. I'm going to stop sharing my screen now so I can wave my hands. There are certain problems which are referred to as ill-posed, meaning if you add or ill-conditioned, ill-posed, it means if you add a little bit of noise to the problem, then the problem goes cattywampus and no longer works. For example, if you took statics, this is a little plug USB charger. If I put it on the back of my hand and you were to draw a force diagram, what would you draw? You would draw a force going down, which is gravity. You would do a force going up, which is the resistance of this by my hand, and those sum to 0. So the sum of the forces is equal to 0. So what do you include about the motion of this object? It doesn't move, right? You have to have a force on it in order to get it to move. So does this always apply? let's apply this now to a pin here. And I put the pin on the bottom on my hand. And if you look at it, you can ideally say that, you know, if what happens if I move my finger? Well, there's a force pointing down, right? And there's an equal and opposite force pointing up, correct? So if I let go of this pin, it's going to stay there. It's not going to move, right? No, we know that that doesn't happen. It falls over, doesn't it? It falls over. So this is an example of being ill-conditioned, that a little bit of uncertainty in your model, a little bit of uncertainty in your model is totally destroys it. And that's what happens as you get closer and closer to the Nyquist rate in this reconstruction formula. Does that make sense? I'll give you another example, and I think this is a fascinating example. I hope that you find it fascinating also. But there was a, okay, I want to do a new screen. Where's my new screen? New screen, new screen, new screen. Clear, that's good enough. Yeah, here is the idea. And this is fascinating. I don't know if you remember, but if we have a band limited signal, so here's a band limited signal. And you Fourier transform it, and suppose that it is band limited, that it goes from minus B to B. Is that okay? Now I'm going to state this without proof, but in the book, it turns out that anytime you have a finite energy or finite area band limited signal, that this is analytic. Do you remember what an analytic function is? It's a function that can be expressed as a Taylor series. So if you take any point here, say t is equal to c, you can expand a Taylor series about this point. And if the function is analytic, it will converge everywhere. Now, when we talked about analytic signals before, we didn't elaborate on them very much, but analytic signals are smooth. So are band limited signals. And it turns out that all band limited signals are indeed analytic. Now, all analytic signals are not band limited, but all band limited signals very smooth. Why does it have to be smooth? Because you can't have any jumps, can you, anywhere? Because if you had a little jump, that would introduce a high frequency component and it would no longer be band limited. Well, this being the case, we have an interesting problem. And I'm going to outline the problem as it was addressed by David Slepian, a Bell Labs engineer, who answered the problem, and we'll show why he answered the problem. Suppose that you are on a cell phone conversation with your grandmother, and suppose that we are going back 20 years. And 20 years ago, you used to be charged per minute for the amount of time you spent on the cell phone, okay? So you would like to limit your conversation length. Well, this is really good because what you do is you get on the phone and you talk to your grandmother, and whatever you say is going to be band limited because, again, you can't hear above 20,000 hertz, right? And maybe there's signal processing in there which chops off any frequencies above 20,000 hertz. So here's the quandary. You can say, "Hi, Grandma, how you doing?" and have a 10-minute conversation. Well, according to this theory, if your signal is band limited, you can go, "Hi, Grandma, how you," and stop the conversation there. And let's just go at this point C, some sort of point C. And could you not, from this signal, compute all of the derivatives at that point? You could compute x of C, in just saying, hello, grandma. You just need that little piece. You can compute the first derivative. You can compute the 20th derivative. And you can compute all the derivatives at that point. Are you following me thus far? And I think you can see where I'm going. If you have all of these derivatives, you can plug all these derivatives in a Taylor series and reconstruct your entire conversation. I want that to sink in because it's profound. And believe it or not, engineers used to be puzzled about things of this sort. Now, the question is, this obviously doesn't work, does it? Why doesn't it work? Can anybody offer a hazard, a guess as to why this wouldn't work?
Infinite number of derivatives?
Well, let's say that I took a million derivatives, and you know that would be good to give me, I don't know, plus or minus a few seconds, maybe, right?
It would be non-causal.
Well, that's another question, and we'll get to that in a second. We'll get to causality in a second.
The value of the derivatives keeps decreasing. When you increase the order of the derivative, it goes smaller and smaller.
Sure, that's fine, but if you knew them exactly, you could still plug them in into this Taylor series and get the expansion everywhere. The problem is uncertainty, and believe it or not, it's exactly like balancing the pen on the tip of my finger. It's exactly the same. Because if you look at this, if you measure your conversation with your grandmother, do you think you could get the value of the function here? Yes. Could you get the first derivative? Could you get the slope? Yes. Could you get the second derivative? Yes, you would maybe fit a parabola to it, right? And you would probably use the parabola in order to generate the second derivative. But third order, fourth order, fifth order, all of a sudden you just get into a quagmire of measurement uncertainty, don't you? And it's because of this noise, this uncertainty, that we have a problem. It can't be done. It's an ill-conditioned problem. It would work if we could get all the derivatives, but in practice, we can't. We can't because of measurement noise, because of measurement inexactitude. And David Slepian wrote a number of fascinating papers to measure analytically this uncertainty. Really, really fascinating stuff. Isn't that interesting, though? But that's an idea of ill condition, just like we get with the sampling theorem for the oversampled signals. When we sample just a little bit above the Nyquist rate, we all of a sudden expose ourselves to noise problems via noise, via any uncertainty in measurement. And again, it's exactly the same as balancing this figure. Yeah, this works fine as long as there's no noise and my model is totally correct, is that I have total symmetry with respect to the pencil and that I can balance it on a point. Sure, why not? Newton's laws say that. But that model is not sufficient enough to take into account any uncertainties that we would have in balancing that pen. Do you get it? The idea of ill-conditioned is something which occurs in numerous cases. And sometimes you might get a solution working out some math and some matrix vector multiplications and things like that. But when you apply it, it doesn't work. And it doesn't work because the problem you're doing is ill-conditioned. I'll give you another example. What happens if you have a matrix? And imagine I'm drawing a matrix here, and the determinant of that matrix is 0. Can you invert that matrix? Nobody knows what I'm talking about? If the determinant of this matrix is equal to 0, can you invert this matrix if A is equal to this? Can you invert it?
No, you can't.
No, you can't. You can't invert it. It's like dividing by 0. But what if the determinant is equal to 10 to the minus 100th? It isn't 0, but it's 10 to the minus 100th. Can you invert it? Yeah, you can, but don't trust it. Don't trust it, because this is going to be a very, what is called an ill-conditioned matrix. Anytime you multiply something by it, by the inverse, just a little bit of tweaking just drives you crazy. Next time we get together, I'll show you an example of this. This is very interesting. So ill-conditioned rears its ugly head another place. So that's interesting. Now, Adam brought up a very interesting point. Any questions on this before I get rid of it? Boy, we got rid of two people, Justin and Aiden. Where'd they go? Their chairs are empty. There they are. Okay, Aiden. Okay, here's another interesting point. These are kind of philosophical electrical engineering questions, if you will. We have a causal signal. We have a causal signal. Could you argue that all signals in reality are causal, that they had to start at some time is equal to 0? You could probably make that argument, right? Are causal signals analytic? No, because if I were to take a Taylor series here for negative time, all of the function and all of its derivatives would be equal to 0. So if I expanded out a Taylor series, what would happen to the Taylor series? It would be 0 everywhere, correct? So any causal signal is not analytic. Well, this is a problem because all band-limited signals are analytic. So this implies that x of t cannot be band-limited. These are examples, by the way, of when theory, if you will, kind of fails us. We need additional insight because we know that we have band-limited signals all the time. So does anybody have a solution to this quandary? Do you understand the problem? If x of t is causal, then we can expand by a Taylor series about the point of negative, and we get 0 everywhere. So if the signal is causal, then it cannot be analytic. And if it's not analytic, it can't be band limited because all band limited signals are analytic. David Slepian also wrote another paper which was called On Bandwidth. It was published in the Proceedings of the IEEE. And he took on this question and he asked himself, well, if all signals are causal, does that mean that band-limited signals are just a figment of our imagination? What do you think? You guys use band-limited signals all the time.
Well, I think when you turn a signal on or off, it has the the high frequency components and all, but then after it's running for a long time, they don't continue to show up.
Or let's say they don't continue to show up, but let's say they diminish.
Sure, yes.
They diminish. And that's the point. Slepian said that, both of these signals, x of t, you could have a signal that was been on for a long time, and you could look at the spectrum, and that spectrum would never go to 0. Never go exactly to 0, but it would have a little bit of energy over here, right? And maybe the percentage of that energy is going to be so small that we don't even notice it. So the models in terms of representation are indistinguishable from each other. And don't forget, we're doing continuous mathematics, and continuous things don't exist, at least to infinite precision. Gregory Chaitin wrote a great story on why real numbers don't exist. Real numbers don't exist because you can't go on forever. If we go into the lab and we put up a voltmeter and say we read pi volts, we don't mean 3.14159 on to infinity. We probably mean 3.1416 or something like that, something which is close to pi, right? So real numbers don't exist. And we're assuming here everything is real numbers. So believe it or not, a lot of this functional analysis that we're doing has some interesting philosophical consequences. We know in practice that when we digitize stuff, that our resolution is constrained by the number of bytes that we allow per sample, as we looked at with the wave function. In a similar fashion, for a continuous function, we're limited by the resolution by our noise, our measurement accuracy. You can never get exact measurement of a quantity. You can only get it to a certain number of significant figures before inexactitude due to measurement uncertainty or the presence of noise or something like that limits your measurement. So we're always limited in terms of our accuracy. And this was the point that Slepian made. He said that, yes, causal signals could be band limited to the point where a causal signal was band limited, and it turns out that the perception, the spectrum in both cases would be, the spectrum of the causal signal would be measurably indistinguishable from a band limited signal. And this is where Adam was going with this too, right? That these little side lobes go away. And how could you measure how far you have to go out for a band limited signal? And by the way, this is a more practical application of a band limited signal. We would say that this was from minus B to B, but actually that never exists. We're going to have a little bit of slop over here because all signals have to stop and start. But we would like that slop to go away. And how could we measure that? Well, the energy of the signal is equal to this, right? And what is the energy of the signal within the band? The energy of the signal within the band is equal to minus B to B exactly the same, except the limits are from minus B to B. Is that okay? And when these are about equal to each other, in other words, the energy outside of that is about equal to 0, we can say, they're the same. So we can assess the equivalence of two signals by comparing their energy and saying if the energy is close enough, yeah, they're the same in terms of the ability to measure them. But the fascinating thing is, and this is the fascinating thing to me, in the ideal world, causal signals can't be band limited, and band limited signals can't be causal. But we don't live in an ideal world. We live in a real world where indeed they can be equivalent. Also in an ideal world, if you call up your grandmother and record the first part of the conversation, a Taylor series says that you can generate the whole conversation. In the ideal world, yeah, that's possible. In the real world, it isn't because of magnitude. The magnitude result. Here's a very interesting example. And this goes to the causal, and this is the one that Slepian talked about. Suppose you have a coax cable, and those of you that are in microwaves know more than I do, and it's a really long coax cable, right? And you put a frequency here of some sort of frequency, you're going to get out the frequency on the other end. I actually should have used U here, right? So out here, you're going to get, if you put in a frequency, no, I shouldn't use U, I should use nu. So what happens, you're going to get out something which is related to the frequency response of H of nu, right? And if you vary the frequency, you're going to get the frequency response of the coax cable. But let's take this up now to optical frequencies. So we try to shine a flashlight down the coax cable. Is anything going to get through? No, nothing's going to get through. Nothing's going to get through. But the flashlight that we turn on that comes out here is, my goodness, this is going to be a causal signal. Anything that we put in is going to be a causal signal, but the output itself has to be band limited. So here we have another quandary. We have causal signals which are placed into a system which is clearly, ideally, low-pass filtered, but it never works out exactly. So these are straining at gnats, and I think the practicing engineer probably doesn't need to know these things, but if you get more into the philosophy of signal processing, it's I think, very interesting. And you can pose to your colleagues that band-limited signals don't really exist, and then get into an argument with them and see if they figure out why, indeed, they do exist in terms of the modeling. Okay, any questions? I really went down a rabbit trail here, but it's fun stuff.
I'm glad you can't get, everything ever will say based off derivatives of saying hi, Grandma. But yes.
I know, but isn't that just a fascinating observation? And believe it or not, engineers and physicists used to deal with this problem until it was pointed out, no, you can't, because of measurement, the finiteness of measurement accuracy and the existence of noise, and in digital signals, the finite bit size of samples. So really fascinating stuff. You're not responsible for anything that I just talked about in terms of ill-conditioned signals, but I think nevertheless it's interesting. And the entire thing that drove this, by the way, was the equation that we generated here. Was this R over 1 minus R, because we see kind of a microcosm of this ill-conditionedness presenting itself here with this R over 1 minus R when the denominator is equal to 0.00000001. When you're that close to the Nyquist, this just doesn't work. But clearly, if you get up to points where R is equal to 0.5, or probably even 0.1 or 0.6 or something like that, this will work. But you're going to have a gradual degradation as you get closer and closer to R is equal to 1. Okay, let me just walk through this last one. Is x of t equal to 1 a band-limited signal? Yes, it is. We answered this already. And in that case, is this true? If the oversample band-limited signal with all of the x's set to 1, does that converge to 1? And the answer is yes. Another interesting property of the sync signal. It always adds up to 1. Okay, any questions with the homework at all? Okay, I'll be giving you some additional homework post haste, so be prepared. Okay, with this now, I'd like to go into a little bit more of the mathematics associated with multidimensional signal processing. We've had a lot of fun to this point with the multidimensional signal processing in terms of playing tic-tac-toe, visualizing higher dimensions, etc. But I want to go into the nitty-gritty of the representation of higher dimensional signals. And we're going to start out just immediately with the idea of a multidimensional signal. And this multidimensional signal is x of t. And this x of t with the vector over it is a vector. And it is multi-dimension. So for example, for n is equal to 2, and that's the parameter that we'll use for the dimensions. For x is equal to 2, this might be x of t1 and t2. So we can write out x of t either in the compact form using the vector, or we can spell out all of the letters. I think it's easier to use the vectors, however. And we'll find out that it's a very utilitarian way of treating this. So we have, and what does this mean? Well, if I have a black and white image, then that's a two-dimensional function. A function means that at every coordinate, at every value of t1 and t2, there's a number assigned to it. So if you go to a picture and you go to the coordinates t1 and t2, there's a pixel value assigned to it. So notice that even though we're using the variable t, that this can be a spatial variable. So t1 and t2 could be x and y on a grayscale image. With that, I asked previously, is the screen that you're looking at currently a two-dimensional function? The screen that you're looking at right now, is that a two-dimensional function? Anybody hazard a guess?
Good. No, it's three-dimensional.
No, it's two-dimensional, but you have three two-dimensional functions. You have three two-dimensional functions, depending on how you divide the image. You can have the RGB. That sounds like a Supreme Court justice, right? RGB, red, green, and blue. You could have an RGB sort of decomposition or the other decompositions that you have, but ever how you cut it, you have three different functions. So you have, in two dimensions, you have one function for the R, one function for the G, and one function for the B. Do I have that right, RGB? So we have three two-dimensional functions. And many times you can concatenate that, but that's a grayscale image would be an example of a two-dimensional function, wouldn't it? And again, x and y would correspond to the coordinates. Now, in the old days when we took photographs that were continuous and analog, then that would be a continuous function. Of course, today, the screens that we're looking at right now are digital, so the screen is digitized, and we'll talk about that in a second. So that is t. So doesn't this look a lot like the regular Fourier transform that we talked about? The answer is yes. One of the interesting things is that it looks like we're doing e to the minus j2 pi u, and u here is going to be equal to, let's see, do I have that on the next slide? I'm not sure. No, I don't have it on the next slide. Okay. So u, the vector u is equal to u1, u2, all the way up to u sub n, where n is the number of dimensions that we're having. T, on the other hand, is equal to t1, t2, all the way up to t sub n. Is that okay? So those are the vectors. And by the way, I like my vectors to go up and down. So I'll put a T here for transpose. So the actual vectors themselves go up and down. Is that okay? And it looks like here that we have a little problem possibly because we have the U transpose times T. It looks like we're raising E to some vector power, but in fact we're not, because U transpose T turns out to be a fancy way to do a scalar. So we're doing the U1, U2. Let me just do it for, well, no, I'll do it for the whole thing. U sub n, that's the U transpose, times T sub 1, T sub 2, all the way to T sub n. So that's what this thing in the exponent looks like. And you notice this is nothing more than U1, T1, plus U2, T2, plus all the way up to U sub n, T sub n. Right? So therefore, it looks like there's vectors in the exponent, but we don't allow vectors in the exponent because for what we do, the exponent must be dimensionless. So we have that's dimensionless, and we can see that this is what it corresponds to. So this works out very, very nicely. We denote the shorthand x of t, right left arrow, to big X, just like we did in the one-dimensional case. These correspond to, this corresponds to a multidimensional, n-dimensional Fourier transform. It's simply a short notation for it. There's some things that we haven't defined here yet. We haven't defined the integral over t. What does that mean? And what does this differential dt with a vector over it means? We have to define those separately. It turns out that the integral over t means n integrals. It means we integrate over all of the values of t. We integrate over t1, we integrate over t2, all the way to t sub n. So this is a shorthand notation which keeps us from writing down n separate integrals. Okay? In a similar fashion, this dt here, by our convention, is written as the differential as the product of the individual differentials, dt1, dt2, etc. And we will find out that we get a lot of utility out of this notation. It's very compact. It looks exactly like the one-dimensional Fourier transform counterpart. It becomes the one-dimensional Fourier transform counterpart when we go down to one dimension. The one-dimensional Fourier transform is a special case of this multidimensional transform, as we expect that it should be. And then lastly, I just wanted to write out what this integral looked like in the case of 2 dimensions. Many times in books, such as Fourier optics, if you take Dr. Who's class on optics, you'll see Fourier transforms of this sort. If you deal in radar and look at far fields, you will find 2-dimensional Fourier transforms. And they typically write out the Fourier transforms in longhand. That is, both the integral side, both of the integrals, they spell out, both of the integrals are here. They spell out the vector t. Instead of just putting a vector, they put t1, t2, and they expand the UTT. They expand this part of the Fourier transform into the summation of these parts. So again, 2-dimensional Fourier transforms are very ubiquitous in physics and image analysis. Okay, any questions at all? So with this, we can talk about a few things. Let's talk about we can talk about a bunch of things. We're going to be visiting a lot of these theorems. And just like in the one-dimensional counterpart, or the one-dimensional case, there's lots of theorems which you can do to manipulate Fourier transforms. Some of these are straightforward generalizations of their one-dimensional counterparts. And you will hear me say that a lot. This is a straightforward generalization of its one-dimensional counterparts. For example, here's the definition. We've seen this. We know that it's linear, that the summation of weighted signals is going to Fourier transform to the summation of the weighted Fourier transforms. So we can apply this. It's very, very nice and useful. We have something which, inversion. And inversion is just like the one-dimensional counterpart. Do you remember that in order to get the inversion, you use the plus j instead of the minus j? Right? It's the same thing here. We use the plus j instead of the minus j to get us from the frequency domain back into the time domain. So that's the inversion formula. And then there's the shift theorem. It's exactly the same as this one-dimensional counterpart. We will talk a little bit about what it means to shift in higher dimensions. Then all of a sudden, we get into things that we don't see in one dimension. We get into something which is called separability. And we will talk about separability, that if you have the product of two one-dimensional functions, one is a function of t1, the other one is a function of t2, and we multiply them together, then the Fourier transform, their Fourier transform is the product of the one-dimensional Fourier transform with the other one-dimensional Fourier transform. If that slipped by you quickly, we will talk about it. We will talk about it more in depth later. Then here's the very interesting question. What is, for example, we know what x of t is. What happens if we multiply this by a matrix? And I usually underline my matrices because I can't make them bold when I write them out. So what is x of a matrix multiplied by t? You know what we'll find out? That if we have x of t, And let me address this from a two-dimensional perspective. If we have an x of t and we multiply it by a matrix, it turns out that we can think of x of t on a rubber sheet. And we're going to thumbnail the origin down. The origin is not allowed to move because you notice both of these are equal to each other when t is equal to 0, right? When t is equal to 0, both of these are the same. So the origin is thumbnailed down. And on this rubber sheet, what the A does is it takes that rubber sheet and it stretches it and it twists it, and sometimes even flips it around. And so that's the consequence of multiplying by the vector, by the matrix A. And we will talk about that more in depth as we get to the rotation scale and transposition theorem. Then we have regular results. We have the convolution theorem, one-dimensional counterpart, and we have the modulation theorem, which means if you multiply in one domain, you convolve in the other. And that's just the Fourier dual of the convolution. But I think the interesting ones that we'll spend maybe the most time on is separability and rotation. Because, well, separability and rotation, scale, and transposition. And these are the more interesting theorems which give us greater insight into the Fourier transform. And just like we saw with the one-dimensional Fourier transform, understanding these theorems give us a domain expertise of having to think about multidimensional signals, especially in the spectral domain. Yeah, multidimensional Fourier transforms are ubiquitous. They occur in nature, they occur in acoustics, they even occur in image compression. You familiar with JPEG images? Do you know that JPEG images use a form of the Fourier transform in order to encode images? And we will spend some time talking about that. JPEG images are, of course, lossy, and that's okay. We use a very clever way. JPEGs are very interesting, and we'll show the technique that the Fourier transform, or relative of the Fourier transform, is used to encode JPEG images. So let me end up by talking about shift. What does shift means? This is an example of shift in 3 dimensions. Right down here, and we're going to be using stuff like this a lot. Right down here, we have a box at the origin. Now, this is not a 3-dimensional function, but I want you to think when I write things like this, that this is a function that's equal to 1 inside the box and 0 outside the box. Is that okay? It's equal to 1 inside the box and 0 outside the box. And we do this because it's easy to draw. And then we have a shift from x of t to x of t minus tau. Now you notice that tau is composed of tau 1, tau 2, and I don't have it here, but there's going to be a tau 3 too, right? And that gives me the vector tau. Those are the components of the vector tau. And x of t minus tau simply means that we take this function and we translate it to, we translate it so that the new origin is at tau. The new origin is at tau. That's it. So this is shifting in 3 dimensions. I think you can see it in 2 dimensions. We would take a 2-dimensional object and we would just shift it so that the new origin was wherever tau said it would be. So this is an example of a 2-dimensional shift, or 3-dimensional shift in this case. And we will deal with our first Fourier transform theorem in multi-dimensions. We start with the definition of the Fourier transform. This is the definition. Notice I'm using the dummy variable here, c, right? Remember, it doesn't matter what I integrate over. It doesn't matter what I integrate over. And then what do you think I'm going to do down here? I'm going to set c is equal to t minus tau. Now don't forget tau here is equal to a constant, right? So that when I do the derivative, or the differential, I should say, that dc is the same as d tau. I think this should be t plus tau. I like it better here. It's more obvious here. T is equal to c minus tau, right? if you look at the expression on the top, going from here to here, we're setting t is equal to c minus tau. And that's the same as thing as saying c is equal to t plus tau here. So making that variable substitution gives us to here. Now we know that we can take this and we can write it as e to the minus j 2 pi u transpose t times e to the minus j 2 pi u transpose tau. Correct? And then this part can be placed outside the integral, and what's left inside the integral is the definition of the Fourier transform. And this is exactly the same steps that we would go through for proving the shift theorem in one dimension. Exactly the same steps. So this is not stretching the brain at all from our previous experience, from our previous analysis. Okay, with that, I see our time is up, and we'll continue on this next time. Are there any questions at all? Or is your mind fried? Okay. I don't know if my mind is fried, but it's been a long day, and but it's always a delight to talk to you, gentlemen. So we will see you soon. God bless.
Thank you.
Thank you. God bless you.
Thanks.
Oh, Dr. Marks?
What'd I do?
Oh, nothing. I was just wondering if you
Okay,
had time
hold